You've been warned many times not to use an extension cord in the manner you're about to see. I plug in one item, the extension cord is all right. Plug in another one. The extension cord is all right. Now these are two small items. Plug in another one. The wire is starting to get a little bit warm. Plug in another one. The wire is really warm now. Watch what happens when I plug in this last one. It's obvious that the results could be very, very dangerous. Of course, I suggest that you don't try something like this. It's really a mess. Now, the wire burned because I overloaded the circuit. Remember, overload simply means that the demand for power is greater than the conductors can handle. In this case, we exceeded the power rating of the wire, and of course, it went up in smoke. I have a demo that will show why this happened. Now, I'll be using a DC source, but the principles are the same as it is with AC. This battery will supply the power. This represents the extension cord with the multiple sockets. This meter will monitor the current we're demanding, and we'll use bulbs to represent the various items demanding power. Okay, I'll plug in the first one. Notice the current it requires from the source. Now, watch current as I plug in another one. Current increases. And also notice what we've done. Both bulbs are across the power source. So we're adding components in parallel. When I add another bulb, current increases again. And it's obvious that if enough components are added in parallel, we could demand more current from the source than even these wires could handle. Well, that's exactly what happened before. Although it's quite a mess, this is a parallel arrangement. So all of the items that we plugged in are in parallel. And as each was turned on, more and more power was required. We finally exceeded the rating of the extension cord wires. It became hot enough to burn the insulation and eventually short out the wires. Now, from this, we should realize that the number of components in a parallel circuit determines the power demanded from a source. Let's go into this further and find out what determines power in each branch of the parallel circuit. And I have another trainer that will show this. Okay, I'll make the voltage connections first and close the switch. Now, we know that power is a measure of how much work is accomplished in a given time. Here, the work being accomplished is the production of light by the filament in each bulb. Then we can say that the amount of light is an indication of how much power is used. With this in mind, then, let's see the factors that determine power. Notice that each bulb is producing a certain amount of light. If I decrease current by changing this rheostat, less light is produced. The filaments are dissipating less heat, then less power is being used. If I increase current, more work is being produced, so power increases. Less current, less power, more current, more power. Then current and power are directly related in a parallel circuit. Another factor that determines power is voltage. Now, to show this, I'll use these bulbs, which are wired in a parallel arrangement, and two different batteries. Now, if I connect the bulbs to this 12-volt battery, notice the amount of light being produced. We can say then that the filaments are dissipating a specific power. But when I connect the same bulbs to this 6-volt battery, well, you can just barely see that they're glowing. So I'll disconnect them. There they're not glowing. There they're glowing. It's pretty obvious that there's very little light here. Then the bulbs are dissipating much less power. Less voltage, less power. More voltage, more power. Then power is directly related to the amount of voltage. Okay, resistance also determines how much power is dissipated by a branch. Now I have a different trainer to show this, so let me change out the trainers. Of course, first I'll make the voltage connections and close the switch. Now, in this circuit, these two bulbs are dissipating the same amount of power. We know this is true because the current in each branch is the same, and the voltage across each branch is the same. Now, I'll replace this bulb with one that has a smaller resistance. Notice that the smaller resistance caused the current in this branch to increase. Notice also that this bulb is brighter. It's dissipating more power. The smaller the resistance, the larger the power dissipated. Remember then, the power dissipated by a parallel branch is determined by the applied voltage, branch current, and branch resistance. Also, the total power dissipated by a parallel circuit is equal to the sum of the power dissipated by each branch. We saw this in the beginning of the lesson. Now, also, you must be careful not to add too many components or you could exceed the power rating of the circuit wiring and, of course, burn it up the way we did in the open. Next, let's place some troubles in the parallel circuit and develop the symptoms caused by an open and a short. As I make the voltage connections, let's notice that the circuit we'll be troubleshooting contains 3 parallel resistors with a meter to monitor total current. Okay, I'll close the switch. Let's start with an open in one of the branches. Now, I'll open this middle branch, and the first time I'll do it here so that we can visually see the indication. You see that there's no current in this branch. The bulb isn't burning. Let's try it again. Now, this time, notice that when I open it, it will have no effect on the remaining branches. I open it, current is still flowing in them. Then one symptom for an open is no current in the branch that's open. Now, I'll reconnect it and we'll see what indications we get from the meters. Let's try the ammeter first. Watch total current as I open the branch, and this time I'll open it by removing the bulb. Total current decreases. Well, let's see that again. There's total current with all 3 branches in. When I open one branch, total current decreases. Then with an open, there's no current in the branch that's open, and the total current decreases. Next, let's try the voltmeter. Since the applied voltage is felt across each branch, we'll have to use a range that will measure the applied voltage. And in this case, we'll use the 50-volt range. Of course, the function switch is on DCV. Okay, I'll connect the meter across the center branch. And as always, when using a voltmeter, you must observe polarity. So I'll go directly across the bulb socket. We see with all 3 branches in, there's about 12 volts across this branch. Remember the middle set of numbers on the DC scale. Watch as I open the branch. The meter's still reading about 12 volts. There's 12 volts with the branch in, 12 volts with a branch open. Then it's pretty obvious that a voltmeter can't be used to locate an open in a parallel circuit. Then let's use the ohm meter. I'll change the function switch to ohms, and we'll use a range of ohms times 1. And as always, we must check meter 0. It's a little off, so I'll 0 it. And also, anytime we're using an ohm meter, we must remove power from the circuit, so I'll open the switch. Now I'll connect directly across the bulb socket. we get a reading of about, let's call it 34 ohms. We're on the ohms times 1 range. Now let's think about this reading for a moment. If we're checking across an open, which should be an infinite resistance, why do we get a resistance reading? Well, let's check the meter connections. This side of the meter is connected through the wiring to each side of the good bulbs. This one is connected through the wiring to the other side of the bulbs. So actually, we're reading the resistance of the good branches. Okay, now let's try this again so that we can pinpoint the ohm meter indication for an open. This time I'll put the bulb back in, and notice the resistance reading with all 3 bulbs in. It's a little over 20 ohms. Now watch when I open the branch. Total resistance increases. Then the ohm meter symptom for an open is an increase in total resistance. Now, if you can't visually check and find the open, you must isolate and check each component with the ohm meter. Let me show you what I mean. For example, if I physically disconnect one end of this branch, I'll isolate it from the rest of the circuit. Now, you watch the meter reading when I do that. I isolate the suspected component, and the meter indicates an infinite resistance. It indicates that that is an open branch. Now remember this about an open in a parallel circuit. A voltmeter can't be used because the applied voltage is always across the branch. An ammeter shows a decrease in total current. Remember, this is because there's no current in the open branch. And an ohm meter shows an increase in total resistance. Okay, let's look at a shorted branch. Okay, I'll remove the ohm meter and return the circuit back to normal. Put this bulb back in and reapply power. Now first, let's notice that if a short were to occur in any of the branches, we're providing a very low resistance path for current. Of course, this pencil is simulating the short. We're effectively placing a wire across the battery terminals. Of course, this means a very large increase in current. But if this circuit is designed properly, what should happen when the short occurs? Well, if this fuse is the proper size, it should blow and protect the circuit components from the excess current. Let's see if it does. Now, I'm going to place a short across this bulb, and first, let's watch the fuse when I place the short across it. See that flash? That indicates that the fuse blew. Well, let me put in another fuse, and we'll try it again. Now, watch for the flash when the short is completed. Okay, there it was. Now, let's do it one more time, but this time, let's watch the ammeter and the fuse. Now, watch carefully. You should watch for a sharp rise in the current when I make the connection. Did you see the needle peg and then fall to 0 when the fuse blew? Well, let's try it one more time so that you can see it. Remove the bad fuse and put in a good one. Now, watch the meter closely when I make the final connection. Okay. It rose sharply, then fell back to 0. So the fuse is doing its job. It's protecting the components. Now, where do we go from here? There's no current, so the ammeter doesn't tell us which component is shorted. And with no current, there's no voltage across any of these components, so a voltmeter won't tell us anything. Then that only leaves the ohm meter to troubleshoot the short. So let's try it. Before I do, of course, I must check the meter 0, and it's still all right. Now, to make sure that there's no power over here, I'm going to be doubly safe and open this switch. Now, I'll check directly across the short. One lead there, one here. Well, you can see that we get an indication of 0 resistance. The short has reduced the total resistance in the circuit to 0. Now you can see why the fuse kept blowing. With 0 resistance, the current tries to exceed the rating of the fuse, but it blows and protects the circuit components. To locate the component that's shorted, if you can't visually see which one is shorted, you must isolate and check each component, but this time, of course, you're looking for one with zero resistance. Let's go over some of the points that we should remember about power and troubleshooting in a parallel resistive circuit. Remember, the power dissipated by a branch is dependent upon current and voltage. The larger the current or voltage, the more power dissipated by the branch. Also remember that the largest resistance dissipates the least power. In troubleshooting the circuit, here's what we found. When we opened a branch resistance, this happened. There's zero current in the branch that's open. Total current decreases because of an increase in total resistance. When we placed a short in the circuit, these are the symptoms that we found. Total resistance is zero, and current tries to go to an excessive value. But remember also that if the circuit is fused properly, it should blow and protect the circuit components. Now remember also that you can't haphazardly add components in parallel, the way we did here. If you do, you could demand more power for the components than the circuit can handle, even though it is fused properly. And you could end up with results like this. Remember, the more components there are, the greater the power dissipated. In our next lesson, we'll look at bridge circuits, a specific use for a parallel resistive circuit.